And that explosion, obviously, it burns pretty hot at like something like 700 million degrees Fahrenheit. So some crazy high temperature. And it makes the star appear very bright. So we've observed these novae all over the galaxy. Now let's watch that again without me talking over it so you can get a sense of how it goes from start to finish. We've got this binary star system. The material falls onto the surface of the white dwarf, and then that material heats up until it explodes, just like you're seeing here. All right, we did it. And that material, as you can see in this video, gets pushed out into the galaxy. All right, now let's get back to the presentation. Or let's try to anyway. We did it. Okay. There's where the YouTube video would have been. Now that, like I said, is called a nova. What's making that sound?
It's YouTube step-line.
Guys, I am so good at my life. All right. Back to normal. Okay, now can you see the presentation again, or do I need to redo it?
You have to.
Golly Moses.
Science!
I promise. This is exactly what you would expect to happen for an adult interacting with technology in front of younger people, right? Like, I'm not that much older than you guys, and I promise I'm not bad at technology, but okay, there we go. All right, so these things are called novae. Now, you guys have probably already heard about supernovae. Yeah, is that correct? Yeah, they're pretty big deals, right? You hear about these huge explosions that happen on stars. And you may have also heard about regular classical novae, but I'll tell you a little bit about the difference between a nova and a supernova. So these are obviously they're not photos or anything. These are just artist pictures of novae and supernovae. And you can see there are there's a big difference right off the bat. This picture on the right of the supernova, the star is actually consumed in the explosion. So a supernova happens on a star, and it could even be a star that's a white dwarf, like in the nova scenario. But the explosion has so much energy in it that it consumes the star. The star is destroyed, more or less. And the supernova can't happen on that star again. But as you saw in the nova video that we just watched, that material, all that happens is it blows off the surface of the white dwarf star. So the nova can actually recur over and over as long as there's material coming onto the surface of the white dwarf from the main sequence star. And again, main sequence just means it's a star like our sun. So it's a star like our sun and a white dwarf star. Okay, so we have novae. Now, like I said, these novae explode and push material off of them. Did everybody see that cool animation?
Yes.
Did it come through?
That's cool, yes.
Great. It's cool. Thanks for affirming me. So it's, yeah, all right, so the animation went off. The nova explodes, and you guys know that space is pretty cold, right? So even though that explosion is really hot, the material that comes off of the nova, it cools off relatively quickly. And all of that gas, that material that's there, it can condense, and it can form little grains, like the ones that you're seeing around the screen right now. Now, those grains, because they're being shot out of the nova, they can basically go more or less anywhere in the galaxy. They just keep going. And they can fly, you know, all over the galaxy. They can fly into other solar systems. They can end up on other planets. Things like that. They can even end up in this. You guys know what this is, right? Any takers? Anyone?
Ride those baby miles.
This is a meteorite. I'm sure somebody said it and I just couldn't hear it. But this is a meteorite, yeah? So this is a piece of rock that fell to the surface of Earth from space. Now, I don't know if you can see it on the screen or not, but in this meteorite, there are these little white dots. All over the meteorite, there are those little grains that show up as those white dots. Now, this meteorite, it fell in Australia. It is called the Murchison meteorite. I think it fell in, like, 1969. And then, we recovered it, pieces of it, in Australia. And what scientists here on Earth can do is actually take bits of that meteorite and analyze it in the lab. So we can use acid or shoot it with lasers or something to dissolve away parts of the meteorite that we don't want until all we have left are these little grains. And if you remember, I said that those grains can come from places like classical novae. So that means they didn't originate in our solar system. The rest of the meteorite might have cooled in our solar system and been created when the planets were forming, but this grain came and fell into that material from some other place. So that means if we figure out what's inside of that grain and it looks different from what we see on the surface of the Earth or what we see around our solar system, we can have a pretty good idea about what sorts of elements we can find and what sorts of chemical processes happen in, for example, classical novae, or really anywhere out in space where these grains can form. And just for a bit of reference here, this grain on the right-hand side, this grain is about 1 micrometer long, which is about the same size as a red blood cell. So these grains can be really, really small. But even though they're really small, they still have enough information in them for us to figure out that they come from novae. They have different elemental abundances. They look different from things on Earth. Of course, the real question is, how can we be certain that they come from classical novae or from anywhere else? We don't know ahead of time that these grains that we discover come from any one place. So to do that, we need to, like I said, figure out what their elemental abundances are. Now, you guys all know, I'm sure, the periodic table?
Yep.
Yes? Heard a yes? Great. I'm going to take it. Now, here's the periodic table, and you can see this square here should be a little bit higher, sorry. But you can see, carbon, for example. Carbon has how many protons? You guys know?
6.
6. Yeah, I heard it. That's good. So you know already that an element is defined by the number of protons in the nucleus of the atom, right? So carbon has 6 protons. Carbon will always have 6 protons no matter what. But for nuclear scientists, people like me, we work with a slightly different chart. If I take all of those elements in the periodic table and stack them, one on top of each other, I can then move them from left to right by adding neutrons. And you guys know, of course, protons and neutrons make up the nucleus of the atom. And if I have carbon-12, that has 6 protons and how many neutrons? Anyone want to guess?
6.
6. Yeah, great. You guys are fantastic at basic math. I'm very appreciative. This is most of the carbon that we see in the world is carbon-12. And you can see here that a small percentage of it is carbon-13. But if you add just one more neutron onto that carbon, it becomes unstable, right? So all of these black boxes are nuclei that are stable, and all of the red and blue boxes are nuclei that are unstable. They want to become these black boxes. Now, this whole chart is just called the Chart of Nuclides. It's not super important or impressive. It just happens to denote all of the different configurations of protons and neutrons that we have observed and we study. Now, anyone want to take a guess at what this number next to carbon-14 is?
Half-life.
Yeah, you guys probably already know it really well. This is the half-life of carbon-14, about 5,700 years. Perfect, good. And you can see that as we get farther and farther from these stable isotopes here, these stable nuclei, these numbers in general trend downward, right? So close to stability, we have 5,000 years for carbon-14. But if I move all the way out here to carbon-22, if I keep adding neutrons and keep adding neutrons, that half-life goes to just 9 milliseconds, which means it doesn't stick around out in nature. If we want to study it, we have to make it ourselves. We can't find it. However, these really short-lived nuclei, they also show up in processes like classical novae or supernovae, or even inside stars. all of these really short-lived, rare isotopes, they can be made during astrophysical processes, like a classical nova. So if we want to try and study a classical nova, we can try learning about some of these unstable isotopes. All right, so here's the chart of nuclides. Oh, I forgot I had this dumb title on here. Well, you guys already figured it out. Here is an expanded version of the chart of nuclides, right? So obviously, the periodic table goes beyond calcium, but for our purposes, since we're just talking about classical novae, we're going to stop here. And you can see that this chart only contains nuclei on the proton-rich side, right? So if I go back here, you can see that the blue nuclei are all neutron-rich. They have more neutrons than the stable nuclei. And the red nuclei are all proton-rich. They have fewer neutrons than the stable nuclei. You could also call them neutron-deficient. It's all the same. Does that make sense generally? This is kind of weird terminology, I guess, but
Sure.
Any questions about any of that? We good? All right. I'm assuming that that is a general yes.
Yes, thanks.
Okay, so here's a chart of nuclides for nova nucleosynthesis, and you can see that there are a lot of arrows on it. Does anybody want to hazard a guess as to what these arrows mean? It's not necessarily obvious, so if you don't know, if you don't get it immediately, don't worry about it. But each of these arrows represents a nuclear reaction that happens in a classical nova. So we start with nuclei down here by carbon and nitrogen and oxygen, and then while the nova is exploding during that section that pushes the material outward where it gets really hot, there's enough energy in the environment for these different nuclei to capture protons, right? So if I move up the axis here, I'm adding protons. So each one of these upward arrows constitutes adding a proton to a nucleus. And then each one of these diagonal arrows, I don't know if you can see this little legend here, it's not super important, constitutes a beta decay. Now you guys have heard about beta decay, I'm sure, right? Okay, good. So in this environment, things are so energetic that these nuclei are capturing protons and beta decaying and capturing more protons and beta decaying again, and on and on and on, building heavier and heavier nuclei. And you can see that these arrows, in general, move from lighter isotopes up to the right to heavier isotopes. So here's an example of these decays. For example, I could have a carbon-12 nucleus and a proton, and they collide and form nitrogen-13, right? You can see kind of, it's a little covered here, but there's an arrow moving from carbon-12 to nitrogen-13. Now, did you guys see what came off of that nucleus at the end? I'll play it again. You guys check it out and tell me if you can see what's coming off of it. Does anybody recognize that symbol? So that was a gamma. Have you guys heard of gamma radiation?
Yes.
Yeah? Okay, good. So it's just another one of the types of radiation. And what happens is that carbon-12 meets with a proton, and as you can see, it turns into nitrogen-13, but that nitrogen-13 is excited. It's in a higher energy state. Kind of like if you take an electron in an atom and you move it to a higher orbital or something, right? Then that atom can move from a higher orbital to a lower orbital and emit an X-ray. Well, it's the same thing here in the nucleus. The nucleus can be in an excited state, and it can emit a gamma ray to decay to a lower excited state. So we have a bunch of proton captures all over this diagram, just like you saw right here, right? So that carbon-12 captures a proton. That nitrogen-13 can capture a proton. What is this oxygen going to do? Is it going to capture a proton? No, it's going to beta decay, right? That's the the diagonal arrow. So it'll beta decay. Then this nitrogen here will capture a proton. Then that oxygen will beta decay. And then this proton alpha reaction will occur. For our purposes, that's not super important. But you can also, as you can see, do a whole bunch of other things here. So that reaction, the one that we just saw, where the proton and the carbon-12 meet and combine to form nitrogen-13, nuclear scientists would call that the carbon-12 p gamma reaction, because a proton comes in and a gamma goes out, a gamma ray goes out. Now, like I said, these diagonal, these diagonal arrows are beta decays. So up here, for example, if I have phosphorus, and phosphorus has 16 protons, so this box here, phosphorus with 14 neutrons, is called phosphorus 30, right? That phosphorus 30 can beta decay into silicon 30. And that's not super important. You don't have to memorize all these numbers. The point is just that all of these different isotopes are created just in the hour or so, I mean, the nova happens for longer than an hour, but it happens in a very short amount of time during which that nova is exploding. Okay, so let's zoom in on this section right here. Now, if I look at this phosphorus 30 nucleus in a classical nova, you can see that there are two arrows coming out of it, right? Okay, so the phosphorus 30 can either capture a proton and become sulfur 31, or it can beta decay and become silicon 30. And we, as scientists, want to know which of those things is more likely, because that'll help us answer a lot of questions about how the nova proceeds, and especially what sorts of things can condense in that explosion. And that helps answer the question where those grains come from, the grains that we were talking about earlier. Okay. Oh, my slides are... Okay. So here is a diagram that's maybe a little bit confusing. Each of these data points on this diagram here is a different grain that we've picked up here on Earth and analyzed. So like those grains that came from that meteor, or the meteorite rather, each of those has a specific isotopic and elemental composition, and we can plot those compositions and compare them to compositions of material that we found here on Earth. So remember I said that those grains, they don't look like what we find on Earth? This plot, all it shows is it's got, you can see these two ratios here, silicon 30 to silicon 28. These are just two isotopes of silicon, right? If I go back here, you can see silicon 30, silicon 28. We just took the ratio of those two isotopes in a rock that we found on Earth, and we compared the ratio of those two isotopes in rocks that we found from meteorites that we don't think come from Earth. And you can see that if I move all the way out here, there's a much higher ratio of silicon 30 to silicon 28 on those rocks that come from classical novae. Much bigger than the ratio that we find on Earth. So again, that's how we know that rocks don't come from Earth. They don't look like things that we find on Earth. Okay. So the this reaction rate, as you can see, is important to figuring out exactly what we would expect the ratio of silicon 30 to silicon 28 to be for stuff that comes out of novae, right? So if this reaction happens in a classical nova, and this beta decay is really fast compared to this proton capture, do you guys think a lot of silicon 30 is going to be made, or a little?
A lot.
Yeah, good, great. And conversely, if the rate is really slow, if this beta decay is really slow, we're not going to get a lot of silicon 30. So figuring out how quickly these rates proceed can actually help greatly in figuring out whether or not these rains come from classical novae or not. So as a scientist, it's actually my job right now to help try and figure out how quickly this proton capture happens. Now, obviously, that's not something that I can do by going out into space, right? I can't go out to the nova and measure the reaction rate. So we have to get a little bit creative if we want to figure it out. Now, so like I said, you guys already know about the shells of the atom, right? The electron orbitals. And you know that if we take an electron and bump it from a lower shell up to a higher shell, then we do so by giving it some amount of energy, right? Typically by having it absorb a photon or something. So the atomic energy structure, does that make sense to you guys in general?
Yeah.
Great. Okay, good. So it's actually not so different from the nuclear energy structure. So in the atom, if I had an atom of sulfur-31, or any other sulfur, it doesn't really matter. If I had an atom of sulfur, I could have any of those electrons bump up to another orbital, and that would increase the energy of the atom as a whole. Similarly, if I have a nucleus, I can take any one of these protons or neutrons, and I can give them a bump in energy, and that'll bump the whole nucleus up to a higher energy state. And just like in the atom, where you have discrete shells, discrete energy levels, right, depending upon where the electrons are, in the nucleus, you also have very discrete energy levels, like a ladder, basically. And a lot of scientists have spent a lot of time figuring out for certain nuclei where those energy levels are. It's not clear automatically. You have to do a lot of theoretical calculations, a lot of programming, and then you have to come up with a lot of really interesting experiments to try and study the nucleus to figure out whether those calculations are correct or not. And in fact, even though for this nucleus, this sulfur-31 that's important for the reaction that I want to study, even though it's been studied for over 10 years, we don't even know where all of these energy states are. It'd be like if you were climbing a ladder blindfolded. You don't know where the next rung in the ladder is going to be. You make a guess. You can guess based on where the other rungs are, but the only way you'll know for certain, I guess, is trying to put your foot there. So that's some of what people do when they're studying this nucleus. Now, these energy states happen to be the exact same energy states that the proton and the phosphorus-30 will combine to give you. So remember we had the, earlier we showed that carbon-12 nucleus and the proton, and they came toward each other and they combined to make nitrogen-13. Well, it's the same process here. We have a phosphorus-30 nucleus and a free proton, and the two of those things can combine to give you a sulfur-31 nucleus. But just like in the image that we showed earlier with the carbon-12 and the proton, the resultant nucleus, the nitrogen-13, or in this case, the sulfur-31, is in an excited state. Some of those neutrons and protons are in higher nuclear shells. So that means that those states can decay. And just like if you have an electron in a higher orbital and it decays by emitting an X-ray, right, or visible light in some cases, in the nucleus, an excited state can emit a gamma ray. And that's where the gamma that you saw earlier actually comes from. Now, it can also, this state, in addition to decaying by emitting a gamma ray, it can actually just give up that proton that it just accepted and go back to being phosphorus-30. So there are a number of different ways that this state can decay. And what scientists try to do when they study these problems is figure out all the parameters of this state. What is its energy? That's this ER here. And remember, like I said, that's not known ahead of time. What's the energy of the state? How likely is that state to emit a gamma ray once it's there? How likely is it to emit a proton? And there are some other things too, other parameters involved with studying that state. And as it happens, each of those parameters, the frequency of proton emission, this big gamma here, capital gamma, is just, it tells you how likely the state is to emit a proton, how likely the state is to emit a gamma ray, and the energy of the state. And all of those parameters affect how quickly that proton capture happens, which, if you remember, affects how much of that silicon-30 is produced. I think I can actually just go back and show it real quick. So remember, how quickly this proton capture reaction happens affects how much silicon-30 we get. And again, the ratio of silicon-30 to silicon-28 helps us figure out whether these rocks come from space, or whether they come from classical novae or come from somewhere else in space. So this is all a very convoluted process to try and figure out whether these rocks come from where we think they come from. Now the problem is that both of these nuclei are really short-lived. You saw yourselves when we were looking at the chart of nuclides, the half-lives of some of those isotopes were very short. The half-life of phosphorus-30 is 2.5 minutes. That's not very fast. And the half-life of sulfur-31 is even less. It's 2.5 seconds. So neither of these nuclei is available for us to just go out on Earth and pick up. We have to make them ourselves, which is what we do here at the lab. Now, like I said, I'm a grad student here at the NSCL, and you guys may have been briefed a little bit about the NSCL. Is that true? No, they have not been briefed. Allow me to brief you. So the NSCL is a lab where we have two cyclotrons, and cyclotrons are particle accelerators. Have you guys heard of the Large Hadron Collider out at CERN? Yeah, good. Okay. So the Large Hadron Collider is a type of particle accelerator. They do different science at a much higher energy than we do, and it's not the same type of accelerator, but both what we do and what they do at CERN, at the Large Hadron Collider, involves taking particles and making them move much faster than they move normally. So we produce them here at the lab, and then we accelerate them in these two cyclotrons, and I'll show you a video in a moment, but I just wanted to show you this overview of the whole lab schematic. So hopefully this is not too bad quality, but we have these two cyclotrons that we can use to accelerate particles, and then those particles actually crash into a small metal target, and they break apart. It's called fragmentation. I guess it's exactly what it sounds like. It's like if you took a jar of marbles and you threw that jar on the ground, you guys know immediately what would happen, right? Those marbles would go all over everywhere. They'd go all over the place. And when we fragment nuclei, we get a bunch of little bits of nuclei, some of which are actually entirely new isotopes that we want to study. Maybe not new in the sense that they've never been discovered before, but new in the sense that we just made them just then. And then after that, they go to all of these different experimental zones, and we're not going to get too into that, except for one particular type of experimental setup. But hopefully this video will show. This is just a really quick walkthrough of what we do here at the cyclotron. Oh. Please. Come on. There we go. Oh, media not found. Is this? Oh boy. All right, guys. This video is not working, which I guess sums up my life. So I'm going to go back to this image and I'll just walk you through it. Sorry about that. But imagine we've got, see this little yellow box here? This little yellow box is the ion source. And these guys, they produce a bunch of stable isotopes. Remember when we were looking at the chart of nuclides, we had all those black boxes? And those black boxes were all stable, which means we can create a bunch of them. We have tons of them. and we create a bunch of stable nuclei, and then we shunt those stable nuclei into this pink cylinder thing. This is the K500 cyclotron. This accelerates particles at a rapid clip. The particles get pushed through here to the K1200 cyclotron, and when the particles come out of these two cyclotrons at the end of the K1200, they're going half the speed of light, which is incredibly fast, right? So you can imagine that if one of those particles moving half the speed of light crashes into another nucleus, it'll smash apart. It'll just break into little fragments. And that's what happens right here at the border between the dark pink and the orange. We have a target, which is made of beryllium, which is a very, very light metal. And the beam crashes into that target, produces a bunch of fragments, and most of them we don't even want, which is kind of funny when you think about it. So we make all of these fragments. We don't want probably 90% of them. So we get rid of the stuff we don't want. I don't know if any of you have taken a high school physics class yet. And if you have, maybe you haven't even gotten to this yet. But as it happens, if you put a charged particle, like a proton, in a magnetic field, like if you put it in between two big magnets, it'll actually move in a circle, which is kind of cool. That's how we make the particles go around and around in these cyclotrons in the first place. So we accelerate them using magnets and big static electric charge things. And then we crash them into this target, and then we use this orange section here to filter out all of the particles we don't want using big, big magnets. So we can actually make it so that the particles we don't like that are too light go too far on the inside of the track, and the particles we don't like that are too heavy go on the outside of the track, and the particles that we want, the nuclei that we want to study, they just go right down the middle of the track. We can actually tune these magnets just right, like Goldilocks style. I don't know. It's really pretty impressive, to be perfectly honest, because we have a whole bunch of junk, and from that junk, basically from a whole haystack worth of nuclei, we're picking out one needle and we're sending it down the beamline more or less every time, which is pretty cool. Now, for my experiment, the one that we're talking about here, where we studied the phosphorus-30 proton capture reaction, we sent the beam down this green beam line, and at the end here, you'll see this little green blob here. That is this, or it's close enough to this. All of these machines in here, you can see there's a lot of electronics down here. There's these big tanks. There's this big frame with a bunch of wires on it. All of this stuff is set up to detect gamma rays, which are what come out of that excited nucleus, right? So we actually ended up populating those states, and we didn't do it quite directly. We did it through some other means, but we still populated those same purple states from that diagram before that emitted those gamma rays, and then we recorded all the gamma rays using these big detectors here. So the beam came in, it actually beta decayed, and then those gamma rays hit these germanium clover detectors, which we surrounded the thing with. And this isn't super important in terms of understanding, the physics of the reaction. I just wanted to give you guys an idea of what kind of tools we use to study that science. Because stuff like this is pretty much what most nuclear scientist experimenters use. It's either tools like this to pick up gamma rays, or it's plastic bars to pick up neutrons, or it's a huge apparatus. I don't know if you guys saw it here, but this giant blue thing is a single suite of detectors that are used for a whole bunch of things. All of this crazy stuff here at the end of these beam lines is used for a number of different experimental procedures, and most of it is stuff that has been made specifically for this process. So it's really important to have people, make this stuff by hand so we can do this science. Anyway, like I said, the end result out of all of this is that we record all of these gamma rays, and we can use that, if you remember, let me just go back here. We can use all of the gamma rays we observe to figure out how probable it is that each of these states that we care about will give off a gamma ray in the first place. And that's one of the parameters we care about for constraining that rate. That is science. That's what we do here at the lab. That's been my job for the last two and a half years, is just figuring out those parameters from that. Now, like I said, the ultimate goal is to use all of that information that we get out of that setup with those electronics, to use that in order to figure out whether these grains that we see that don't look like grains here on Earth come from classical novae, or whether they come from somewhere else. You know, they might come from any number of places. And we think they come from novae because some of the things that we see in this grain match what we think we see in novae. But in order to be sure, we have to do these experiments. So that maybe, hopefully, didn't go too fast, and hopefully it wasn't too detailed or in depth. But if you guys have any questions about what we just talked about, I'm happy to answer them. This slide I just put in because it looks cool, but that's the end of my talk. And I'm happy to take questions too.
Well, before we read your question, please.
Oh, it's already over.
If almost every regular novae has heavier and heavier elements being formed as we generate, different generations of stars, what is that eventually going to do to the universe as far as a matter and expansion? And is it going to continually expand, or eventually is it just going to be so heavy that it'll stop the expansion of the universe?
Just pulling out the big questions right on top. Okay. So the expansion of the universe is actually it's above my pay grade as a nuclear physicist. That stuff is is cosmology, right? So the expansion of the universe, it depends on a number of parameters that are actually irrespective of the processes that I study. They have to do with distribution of matter and energy in the universe. So, for example, you guys have, I'm sure, heard about dark energy and dark matter, right?
Yes.
Yeah. Okay. So that that stuff is more what constrains the expansion of the universe and whether or not the universe will whether it will keep expanding faster and faster, or whether it will expand slower and slower until it stops and then contracts again, or whether it'll just keep expanding at a steady rate. That kind of stuff is for when you do your high energy physics webinar. As far as, I think you asked another question about what happens as these materials are being burnt over and over into heavier elements.
Yes.
Yeah, so that's a good question. Each of these novae has a companion star near it, right? So you saw in the video we had a star that was filtering hydrogen onto it, and eventually that star itself is going to stop burning hydrogen. It's going to run out of hydrogen to burn, and when that happens, the classical nova process will just stop that pair of stars. And other stuff can happen.
Have a great weekend.
Thank you.
Thank you. Thank you. Weekend, guys. Place those in our basket, please.